Cameras on. AP stats, we're picking up on the true or false. Principle number one with interpreting confidence intervals is that individual results may vary. The confidence interval has to do with the difference of means, not with an individual. If I eat cat meat, if I eat a meat hot dog instead of a beef dog, cows, not cats, there's a 90% chance I'll consume less fat. Friends, that's false. The confidence interval is about means, not about individual hot dogs. That's why we need that phrase on average, not for every individual. Individual results may vary. B, 90% of meat hot dogs have between 1.4 and 9.5. 90% is not 90% of hot dogs, it's 90% confidence level. That's a false statement. The confidence interval is about means, not about individual hot dogs. Part C, I'm 90% confident that the meat hot dogs average 1.4. Okay, that's a true statement. And D, if I were to get more samples of both kinds of hot dogs, 90% of the time, the meat hot dogs would average, 90% confidence is, what it means is that we're going to capture the truth 90% of the time, not that that particular confidence interval is going to show up 90% of the time. It's a false statement. Confidence intervals based on other samples will also try to estimate true differences in population. There's not a reason to expect other samples to confirm this particular result. Any questions on the true or false activity?
Mr. Roy.
Oh, there's one more, and that is part E. That's a true statement.
Mr.
Yes, go ahead.
When you move up to questions, it has like a parentheses, negative 6.5, negative 1.4. How do you explain what the numbers indicate? Like why is the confidence interval is two negative numbers?
Yeah, well, it's because when we took the sample mean of meat calories minus the sample mean for beef calories, the difference when you performed the subtraction in this order ended up being negative, whatever the average is, looks like about -1. So it looks like it was about -4.4 was the observed difference in sample means. And so that's why, because they're negative, notice that the correct interpretation has the phrase less fat. That's a shout out to the negative side. It's right here. Further questions? All right, so that's comparing means, part 1 of 3. Take a look at the next handout. I'm going to pause while we get set up on the next. And now we're comparing means, part 2 of 3. Our real world connection here is in a factory. A factory is hiring people to work on an assembly line and gives job applicants a test of manual agility. This test counts how many strangely shaped pegs the applicant can fit into matching holes in a 1-minute period. Doesn't sound stressful at all. The table below summarizes the data by sex of the job applicants. Apparently this is a 2-gender view of reality. Everyone's male or female. Assume that all conditions necessary for inference are met. It's an idea that actually is rooted in the first chapter of the Bible. That's where we first came up with this idea of just having 2 genders, male and female. There's a purpose for that. Let's type this into our calculator. So if we want to see, is there truly a difference? I mean, it kind of looks like for males in this sample, it was 19.39 on average for that sample of 50 males. Female average came out lower, but is that difference statistically significant, or is the difference in sample mean something that can be attributed to natural sampling variation? I mean, you wouldn't expect the means to be exactly the same anyway. So, as we look at the AB80 chart, the way that we reduce anxiety when it comes to knowing which of this dizzying array of options do we pick on the calculator to difference of means. You know, we're not trying to capture the true proportion or the true mean. We're trying to capture the true difference in means. And it looks like in this particular handout, which is it? Are we going to build a trap or conduct a test? If you take a look at the directions in terms of what's requested, first we're just going to find a 95% confidence interval for the average number of pegs that males and females can place. Now that's, interestingly, the question is not even asking yet for the difference. They're just saying, let's get a confidence interval for the true mean on the males, the true mean on the females, and check to see if the intervals overlap, which is strange. Why don't we try to build a confidence interval for the difference between the means? Well, that's actually the right thing to do. But what we're doing is we're exploring a misguided way of approaching the problem. And then we're going to find out why it's misguided. So just to let you know, the way we're starting here is showing you that we're willing to empathize with the way that students sometimes think in a confused way. So even though this is not the correct way to approach the problem, let's see what happens if we build a 95% confidence interval for the males and a 95% confidence interval for the females. So just trying to show you the contrast between what we're trying to learn and what students sometimes try to do instead. So let's just try to capture the mean for the males and the mean for the females. Okay, so we can do that. So for males, so the observed mean for the males is 19.39 plus or minus T star for the males, T star sub 49. There's 49 degrees of freedom here, times the male standard deviation is 2.52 divided by the square root of the sample size, square root of 50. So that's what we write down. However, we don't have to type that square root into the calculator. Instead, we're thinking A, B, 80. That would be stat test 8. So we go to stat test 8. And we do actually have the statistics. We have X bar for the males is at 19.39. And standard deviation for the males, the sample standard deviation is 2.52. Okay. 50 is the sample, and they're asking us to build a 95% confidence interval, so let's calculate that. Although I will point out that in the setup, you are responsible for actually doing or finding the value of T star sub 49. That would just be your inverse T of 0.975, comma 49. That would give you this number. That'd be part of the setup. But we got 18.674. Let me see if I can display both of these at the same time. Oh, yeah, it's actually right here. I had pulled it in previously. So we are 95% confident that males can place between 18.674 and
20.106.
20.106 pegs on average. Go ahead and do the confidence interval for the females. Try to build a 95% mu trap for the females based on the sample. Just checking back in here. I'm sure someone's already typed it in, doing a stat test 8. Who can give me the location of the T for the 95% confidence interval for the mean number of females? Yeah, Andrew, go ahead.
95% confident females can place between 16.947 and 18.873.
18.873. So it's 19.947, 18.873 pegs on average. Okay, thank you for that. Now, notice that if you were to place these confidence intervals went together on a number line. For the males, I'm going for blue on the males, so that'd be 18.6, 20.1. So there's confidence interval for males. Confidence interval for females is 16.9 all the way up to 18.8. So people who are confused might say, oh, look, the confidence intervals overlap. Therefore, there must not be a statistically significant difference on average. So those intervals overlap. What does that suggest about any sex-based difference? The fact that the intervals overlap may appear to suggest that there is no difference in the mean number of men. However, that's not the correct approach for this problem. What we should be doing is a two-sample t-interval. That should be constructed to assess the difference in the number, to see if there's a difference in the means. Now, the mathematical basis for criticizing this approach to the problem is that standard deviations do not add. So you can't check for a difference in standard deviations. It's variances that add. If standard deviations don't add, they don't subtract either. We should not be comparing means and whether they're a certain number of standard deviations away from each other. You see, when you're calculating the teeth for the male interval and calculating the teeth for the female interval, you're going out a certain number of standard deviations from the observed means, and sorry, you just are not thinking correctly. So what we should be doing is a 95% confidence interval for the difference. So on the AB80 chart, we're thinking that we're not going to use row 3. We're not going to get a mu for the males, mu for the females. Instead, we should be using row 4. We should be doing a stat test 0. So the correct way to approach this problem, let's do it now. Let's go stat test 0. Let's input the data for the males. No, actually, let's do ladies first. So ladies first. Go ahead and input mean standard deviation 50 for the females, and then men will go second, and it's not stat test 6, we don't pool. Pooling is always no unless you're doing stat test 6. And see if you can calculate the information there. I'll give you a chance to do it. And pause the camera till we're done. All right, we're back. So what we typed in for stat test 0, putting the 0 in AB80 5624. Female data is first, male data is second. We're not pooling because we're not doing a stat test 6. When we calculate, so wow, both numbers are negative. That's an indication of a significant result. And by the way, here's degrees of freedom from technology. The degrees of freedom formula is scary. You don't need to know it. You'll never have to write it down. All you have to do is say there's 90.4858 degrees of freedom from technology. And so let's record our results by pulling this into our document. Okay, so based on what we see on the calculator, we can say that we're going to construct a two-sample t-test, and we are responsible for writing down the given information. Notice how this is documented. AP graders will allow you, in the context of this problem, to just use M for males, F for females. We're doing females minus males. So the way that we set it up, since we did ladies first, it's going to be X bar females minus X bar males. If you have it, which, yeah, so it's already printed in there. So that's why ours came out with negative numbers. Instead of this one here, came out with a confidence interval that was positive numbers. The numbers have the same absolute values. But notice what the effect of changing the order of the subtraction is. So anyway, what does this interval suggest about a difference in mean agility? Well, we're 95% confident that the mean number of pegs placed by males is between 0.29 and 2.67 pegs higher than the mean number of pegs placed by females. Since we did ladies first, the wording would be a little bit different. We'd say we're 95% confident that the mean number of pegs placed by males is by females is between 0.29 and 2.67 pegs lower than the mean number of pegs placed by males. Either one would be correct. You just have to be aware of the direction of the subtraction. Do you have any questions on part D? So yeah, you can record it either way. You just make sure you're aware of the direction of the subtraction. All right, we're going to continue on there. So the results seem contradictory. So now we're getting down to clearing up the confusion. Which method is correct? Doing two-sample inference or doing one sample twice? The two-sample t-interval is the correct procedure. The results don't agree because if you attempt to use two confidence intervals like we did at first, you're actually adding standard deviations, but it's variances that add, not standard deviations. So there's a mathematical reason why the second approach is the correct approach, not the first one. Now,
We have different.
Yeah, we don't have any.
oh yeah, you have a different page too? Let me take a look at that. Okay, yeah, actually all that means is that your page 2 somehow is missing. So what I'll do is I will make a copy of that for you. That interestingly, yeah, you have the, yeah. So tell you what, that's just a theoretical issue, and as long as you understand that the two-sample approach is correct, the problem that we're about to look at, I just want you to view it because it's basically a, why are we not allowed to attempt this problem? So it's not on your handout, but let's look at the job satisfaction problem. Just imagine this. A company institutes an exercise break for its workers to see if that will improve job satisfaction. Forced exercise. Let's see how this goes. People seem to be upset about job satisfaction. They're not satisfied at work. I know. Let's force them to exercise every day, and then we'll measure their job satisfaction again. Everyone, down and give me 20. I can't believe this. And one extra. Now they're going to measure my job satisfaction score. Peter, did you do 20 push-ups also? Yeah. Thank you. I would expect nothing less from Mr. Wow. All right, so now they're going to measure my job satisfaction. You see, I was worker number 5. My job satisfaction score before forced exercise was only 26, but once they started forcing me to exercise, woo! Work, let's do it. Now, other people are like, I'm doing just fine. I love my work. I still like it, but I'm not a big fan. I'm not a fan of forced exercise. Worker number 3, yeah, this was kind of a big deal. Friends, the approach that we just took, stat test 0, find the difference in the means. I mean, we could average these numbers and average those numbers. Why is it a misuse of mathematics to use difference of means to decide whether or not forced exercise is a good idea? To say, okay, well, take the average before, take the average after. Let's find the difference in means. So your conditions. Why would building a 95% confidence interval for the difference in means? Mu1 might be average work satisfaction before forced exercise. Mu2 is average job satisfaction after forced exercise. Why can't we take this approach? Why are we not allowed to build a two-sample t-interval for difference of means? I'm hearing something. What? Why is it mathematically misguided to build a two-sample t-interval for the difference of means to assess whether or not forced exercise increases mean job satisfaction? Once again,
Is that because it is not independent group?
these are not independent groups. The before group is not independent of the after group. They're the same people. They're not independent groups. If you had, one sample, they'd have to be different companies. I mean, you'd have to, it's completely ignoring the independent groups. Now, it would be perfect. This would be a perfect situation to look at the mean of the differences. We could check just get one column of differences, go back to our data and say, okay, let's set up a difference column D. Go ahead and do that. Well, no, you don't have this data, but I'm just trying to show you the big picture. I could do before difference, I have to specify the direction. I could do before minus after. Those would be my differences. 34 minus, actually no, I want to do after minus before. I want positive to mean it's working. So let's do after minus before. 33 minus 34, that's a difference of -1. So here's positive 8. We write down all these differences all the way down to 10. And I want to find mu sub D, the mean of the differences. Not the difference of the means. If you have independent groups, then you can find the difference of the means. But if you have just one group and you're checking before versus after, right boot waterproofing versus left boot waterproofing, that's when you would use mean of the differences. Okay, so now let's go to the problem that you actually have on your paper. And it's, I guess this is what it's come to. Sex and violence. In June 2002, the Journal of Applied Psychology reported on a study that examined whether or not content of TV shows is influenced by the ability of viewers to recall brand names. Okay, so people are watching Netflix. No, they're not, because there's commercials. I mean, last I checked, there's no commercials on Netflix, are there? No. So we're watching non-Netflix TV where they have commercials. And so what they're doing is they're taking 108 subjects. These are independent groups, by the way. These are not the same people. They take 108 randomly selected subjects. Or, no, they're not randomly selected. This is an experiment. We are imposing treatments on them. We're telling them, watch this commercial that has violent content. Other people have been, from the 324 volunteers, 108 of them have been randomly assigned to watch commercials with sexual content, and 108 have been randomly assigned to watch commercials with neutral content. This is while they're watching some other show. And then they quiz them afterwards. How many brands did you recall? All brands of products. How many commercials were there featured in the commercials? I don't know if they tell us how many commercials they watched, but is it 9?
Yes.
Oh yeah. Okay, so there were 9 commercials. So, on average, 2.08. If they're watching violent content, they only remembered 2.08 on average brand names. For the sexual content, not a lot of memory, as for some reason they couldn't remember what was going on in the commercials. With neutral content, it was 3.17. Are these statistically significant differences, or can they be attributed to natural sampling variation? So, A, do these results indicate that viewer memory for ads may differ depending on program content? This is an important study because advertisers might be like, well, wait a second, I don't want to advertise. Oh, it's just the other way around. It's actually the program itself has either violent content, sexual content, or neutral content. So this raises the question, do advertisers want to advertise on a program that has sexual content if people are not going to remember their commercial anyway? So it's not the commercials that have this content, but it's the show itself that has these types of content. So a tested hypothesis that there's no difference in ad memory between programs with sexual content and violent content is P equals 0.136. So you can only compare two at a time. You could do, mean violent minus mean sexual, violent versus neutral, sexual versus neutral. So which ones did they pick? They did sexual versus violent. And is that a statistically significant p-value, P equals 0.136, class? Yes or no? Is it statistically significant?
Yeah.
Andrew, what do you think? Would you say statistically significant, yes or no?
Yes,
Based on what?
based on Kennedy hearsay.
Okay. Now, I want you to base it on your own thinking. If the p-value is 0.136, would that be statistically significant or not?
It's under 0.5. Oh, no.
Is it, you say
Bigger.
it's bigger. So since it's bigger than 0.05, is it statistically significant or not?
So, whoops.
Andrew?
I would say yeah.
No, it's only p-values that are less than 0.05
Okay.
that are statistically significant. So what this means is that these two sample means are not statistically significantly different. It really doesn't matter whether, violent TV shows versus sexual TV shows when it comes to ad memory. Since it's high, we fail to reject the null hypothesis. There is no evidence of a difference in the mean number of brands recalled by viewers of sexual content, viewers of violent content. Okay, now let's go on to part B. Is there evidence that viewer memory for ads may differ between programs with sexual content and those with neutral content? So this looks like the biggest difference in sample means, 1.71 versus 3.17. Test an appropriate hypothesis, state your conclusion. So the null hypothesis is that mean sexual minus mean neutral is 0. The mean number of brands is really the same, and what we observe in this difference is just due to natural sampling variation. What would the alternate hypothesis be? Would we go with, should be, the way we're going to write this is, we'll go with the does not equal to 0, so it's a two-tailed test. Mu sub sexual minus mu sub neutral does not equal 0. Now, there's reason to believe that it would be, we could actually just go plain less than 0, but this is more conservative. Then it's the industry standard, just to do a two-tailed test. Two-tailed test is harder to pass. It's harder to get a result of statistical significance. But here's the documentation. Recall of one group should not affect the recall of another. They're independent of each other. Subjects were randomly assigned. We didn't randomly select them. They volunteered for the experiment because we are imposing treatments on them. You can't just randomly select people and impose treatments. That's unethical in Western civilization. Nearly normal condition, the samples are large, so we're good there. The conditions are satisfied, so it's appropriate to model the sampling distribution of the difference of means with the student's T model. It's really a Gossett's T model, but you know the backstory, with 214 degrees of freedom from technology. So let's find out where that came from. Where did the 214 come from? Well, let's type in the data. Class, let's do a stat test. Going for the p-value. I think we're going for the p-value. So, yep. We're going to do the test statistics. So for the first time in our lives, we're going to perform a stat test, AB 5624. Let's do a stat test 4. So stat test 4, type in the mean and standard deviation for sexual content first, then the mean and standard deviation for neutral content, and
What is this test, Cal?
so stat test 0. What we're doing on the AB80 chart is we're saying, okay, I want to find a test statistic for the number of standard deviations that these means are apart from each other. So,
What is,
so stat test 4, we're doing a 2-sample t-test with a difference of means. We have 2 samples, one sample from commercial brand recall from programming with sexual content, The other sample is for brand recall from television programs that have neutral content. So, what would Stranger Things be? Stranger Things would be violent and, is it considered neutral content?
Probably.
Stranger Things would probably,
But it's on Netflix, no commercials.
yeah, but I mean, but if it were to be shown on network TV with commercials. So yeah, go ahead and run the stat test 4 and let's see what results you get. I'm gonna pause while we type it in. For those of you watching at home, the way that we typed in stat test AB805624, we're putting the 4 in AB805624. Here's the sexual data up top, the neutral data there. We're not pooling. And when we hit calculate, we got a p-value of 5.49 times 10 to the negative 9. That is extremely tiny. It is the way we interpret that is that the probability is very small that we would observe a difference in means as extreme or more extreme than what we observed due to natural sampling variation alone. Notice the degrees of freedom, 214, it comes from technology. If you wrote 213.9931, that would be even better. No one's asking you to use some sort of n-1 formula to get this. It comes from technology. So let's document our report. What we did down here in the purple, we said, since the conditions are satisfied, it's appropriate to model the sampling distribution of the difference in means with the student's t-model. The 214 came from technology. It just came from stat test 4. We're going to perform a two-sample t-test with an alpha level of 0.05. We're setting the limbo bar at 0.05, and any p-value that comes out will be compared to 0.05. So this is the handout that's online, so if you don't quite fill that in, you can go back and it's already posted online. So friends, the sampling distribution model has a mean of 0, so we're assuming the difference is 0. This is the difference between mu sub sexual minus mu sub neutral. It has a mean of 0. What we observed was -6, a test statistic of t equals -6.08. So the p-value, since it's two-tailed, this p-value of 5.4 times 10 to the negative 9th, 5.4 times 10 to the negative 9th, is really the sum of the tail areas together. But notice the documentation that you're required to provide is the setup. The calculator does the rest. So here's our conclusion. Since a p-value is low, we reject the null hypothesis. There is strong evidence that the mean number of brand names recalled is different for viewers of sexual content and viewers of neutral content. Sentence 3, the clickbait sentence. The evidence suggests that viewers of neutral ads remember more brand names on average than viewers of sexual content. If you leave out the on average, your E drops to a P. We're talking about averages. We're not talking about, individual results may vary. There may be some people who can subject themselves to neutral content and not be able to remember anything. Individual results may vary. Homework number 2 is due tomorrow. You are dismissed.
Mr. Reyes.